La la la.
Are we doing practice problems today?
Practice problem?
Like, because I'm a little confused, like, with where, like, how the person gets the 3/4.
Sum n equals 2 to infinity of 1 over n squared minus 1. Okay, let me write. Right, that one? Okay. Let me begin with a word of prayer. I had to write that down before I forget it. If I say any words before I write, it will leave my mind. That's how little it's just bad. But anyway. Dearly Father, we thank you for this day. We thank you for the break, and just ask you to help us to use this time wisely as we prepare for the test tomorrow. In your name I pray. Amen. So one thing I wanted to mention before I forget, and this is kind of a second order comment, but it's worth noticing. We could have been much lazier on the 1 over the natural log of n to the 10th problem if we had embraced exercises 47 and 48. And this is from the handout PDF, of course. This is from his the limit comparison section. But see what he has here? If a series of positive terms, suppose that the quotient limits to 0. All right? Is that covered by the limit comparison test that we talked about? No, it is not. That's past what we discussed. And but what this says is if the quotient goes to 0, then you have the following things. If the denominator converges, the numerator also converges the series. All right. If the numerator diverges, then the denominator diverges. And then C and D are warnings that you have to think about the numerator and the denominator in attachment to their relation to the quotient and its limit. Like you can't. This is the thing. The reason we don't include this in the statement of limit comparison test. I say limit comparison test. How do I say it? I say you calculate the limit of a sub k over b sub k. It goes to L, where L is positive. And then what? The fate of the series are what? Shared, right? This is more nuanced than that. This is saying if the quotient a sub k over b sub k goes to 0, then if you have the denominator is giving you a convergent series, then it follows the numerator is convergent. And vice versa. If the numerator diverges, the denominator likewise diverges, given that the limit of the quotient is 0. This is an extension on the limit comparison test. What do you think exercise 48 says? I'm guessing, I haven't looked, I hope I'm right. If I'm wrong, I'll be wrong, but I bet problem 48 has the quotient of a sub k over b sub k going to infinity. I bet it's the dual to this problem. See, because we worked out, one of the things you guys, yeah, check it out. There you go. So a sub k over b sub k goes to infinity. If the denominator diverges, it implies the numerator diverges, and vice versa. If the numerator converges, the denominator converges. Why would this have been helpful? This would have been helpful because one of you guys told me to do the limit comparison test on the log to the 10th problem, and we got that the quotient worked out to infinity. If we'd known about exercise 48, we'd have been done. That would have worked, right? So, it's a question of pedagogy. Do you want to include this case in what's quote unquote the limit comparison test or not? So what do you guys want for the test? Should limit comparison allow these exercise 47, 48? No? All right. Very good. Well, I will give you the freedom to use the extended limit comparison test if you want, but I would ask that if you're going to do that, you would say using the extended limit comparison test. If you don't say that and yet use it in the extended sense, then I will react accordingly. Anyway, all right. Enough about that. Like way too much about that. Let's look at the solution to mission. What are we on? 2. I'm sorry. In the rush of this morning, I forgot to bring your missions back down here, or rather back up here. I'll bring them back tomorrow. Did you want them to look at for tonight's studying? If you do, just follow me back to my office after class, and I'll let you borrow it. You just got to give it back to me again tomorrow, okay? Make sense? Start a class, you give me back, and I should have all of your mission folders back to give to you by the end of the test tomorrow. That's my plan. But again, if you want to study it, if you want to take it from me and look at it tonight, you're welcome to come get it from my office if that's something you want to do. I don't mind. Let's see here. Where are we? Oh, mission 2 solution now. Are there any particular, well, before I ask if there are any particular problems, let me just say something. So, one of the things that those of you who've asked me something about the test have asked is there going to be a proof on the test, right? Like, what are our proof responsibilities? Well, and so others of you asked me a related question, which is like, why have you put homework problems which are just what you did in class? Right? Like, what's the point of asking a homework problem where the complete solution was given in class? What would the point of that be? To emphasize its importance, yes? Which would suggest what? Well, let me take the mystery out of it for you. If I'm going to ask a proof question on the test, it is very likely to be one of the ones that I have already put on your mission, all right? So let's see here. Did I ask you to prove the geometric series on the mission? I did? Okay. I would be shocked if I didn't. So I remember this much off the top of my head, that the nth term test and the geometric series result, the proof of both of those were problems in the mission, right? So those are 2 tests that I might ask you to prove, right? There's how would you prove the nth term test? What argument proves the nth term test? What is that here? Problem 54, right? So to prove the nth term test, let's look at it. Here's the solution. So if you assume that the series converges, right, and we use S sub n for the nth partial sum, then we use S sub n for the nth partial sum, then we can observe that the difference of the nth and the n minus 1th partial sum is exactly what? It's exactly a sub n. So if we take the limit as n goes to infinity of this, right, we're by assumption, right, by the definition of a series summing to S, or a series converging to S, if you like, we know that the limit of the sequence of partial sums is S. So if we look at the limit of a sub n as n goes to infinity, we have the limit of the difference of this and that, right? But as n goes to infinity, this goes to S, that goes to S, so this goes to S minus S, which is 0, and, well, that's the nth term test, right? If we have a convergent series, the limit as n goes to infinity of a sub n must be 0, right? So that's one that could conceivably be on the test, right? Problem 55 is another example. I might say, you have 2 series, they're both convergent. Prove that their sum is also convergent, and that it converges to the sum of their sums. Now, the main steps in problem 55 are just showing that the nth partial sum of CAK plus BK is C times the partial sum of A plus the partial sum of B. And then to find what happens for the series, we take the limit as n goes to infinity in this and use limit laws to get the result. So what are the steps to prove that the series of a sum is the sum of the series? There's really 2 steps. The one is to identify that it's true for a finite sum, which is this, right? It's true for a finite sum. And then to use the definition of series converging, right? If I give you that this is equal to A and that's equal to B, what does that mean precisely? That means the limit of sequence of partial sums for A is big A. The limit of the sequence of partial sums built from B is big B. And so I can take the limit of this expression. And using limit laws, which you've proved in a previous part of the submission, possibly you've proved it, you get that result. So what does that mean? That means if I was to ask this question on the exam, I assume that you're allowed to know the limit laws for sequences, right? So like the same sort of backdrop for the storytelling in this proof is also assumed for you in the exam, right? In fact, I probably would even write a sentence in the statement of that problem that says, you may assume the limit law for sequences is known in your argument. That's very likely that I would write that sentence if I was to assign this problem. Did I put that in the statement of the mission? I should have, but I mean, I didn't. But, you know, mission problems you can ask me about, so that's a little bit different. Like on a test, you can also ask me questions in the test, right? But you guys just don't, right? I mean, you should, but you don't. There is a kind of question I will answer on the test. There's a kind I won't. And so anyway, I hope that, so let me answer a question that's probably related and very much corollary to what I'm saying, which is, would you have to prove the root or the ratio or the limit comparison test on the test tomorrow? No. I did not ask you to prove those in the homework. We went through them in class, right? Because I want you to understand it's not just a black box. There's a logic behind it. But to my taste, the proof of those theorems is actually above the level of this class. So I expect you to know those theorems and to use them, but I don't expect you to prove them. In contrast, geometric series and nth term test is something I want you to know, top to bottom, the nuts and bolts of, which is why I put it in your homework, and I also might ask you on the test. Of the last 10 tests I've given in Calculus 2 on this material, I think proof of geometric series probably appeared in 8 of them, right? So like from an actuarial perspective, there's a high likelihood of that question. One of the more disturbing things I've seen teaching Math 132 online is asking that question in an open book, unproctored context and still have people not answer it. It's like, what? How? But yes. Unless you think you should take Calc 2 online, I could tell you some stories. It doesn't go well. It does not go well. All right. Anyway, I think hopefully I've answered those. If I did ask you an epsilon n proof, it's likely to be something similar to the ones that you've had in the mission also, right? So what was the point of the bonus quiz, by the way? Do you know what the point of that was? I mean, yes, to try to give you points. That's true. I mean, that is one of my goals. I have failed in that, in some sense. But one of the reasons that I gave you that bonus quiz early on was to alert you to the fact that you actually had not at this time figured out what the definition of the limit of a sequence was, right? The sequential limit. What does it mean? Limit is a sub n, as n goes to infinity, of a sub n is equal to L. Or what does it mean for the sum of the series to be L, right? How do we define these things carefully? I asked those questions on the bonus quiz to draw your attention to the fact that you did not actually know those definitions, all right? I'm not surprised when I looked through these and found that 95% of you did not know the definitions, right? Because this is something weird in math. Definitions matter, right? How many definitions do we come across in calculus? A lot? I would say not that many. It's it's a fairly rare event for me to define something in here. I'm not talking about a result. Like we give a name to a theorem, limit comparison, root test, ratio. Those are not definitions. Those are results. Definition, I mean, what is the limit of a sequence? What is the sum of a series? What's the Riemann integral, right? How do you define a derivative of a function? These are definitions. There really are only maybe about a dozen that you've seen so far, I would wager, that are really native to this course, that aren't something you should know from before. So those things are precious, and you need to know them like precisely. So one of the few things in here I would say you should memorize a version which is true and verbatim, all right? If for whatever reason you're having trouble just conceptually like getting it down precisely, memorize it, right? Memorize the definition for a sequence, the limit of a sequence, the limit of a series, summing to an L, like we talked about on the bonus quiz, so that if I ask you those, you at least get those, and you don't have to feel bad about not getting those. One of the things I would warn you, many of you have, is this your last math class? Some of you, the answer to that might actually be yes. Some of you, the answer is no. I've got like 3 more past this, right? You've got what? You got calculus 3, differential equations, and then what? Possibly math 221 or possibly math 321 if you're in the minor, depending on what you do. When you hit those linear algebra courses, 221 or 321, there is a unending like fire hose of definitions coming at you. It's like definition, definition, definition. You have to start learning to absorb definitions. If you don't, you won't understand what your teacher's saying. That's also true for calculus 3. There's more definitions in calculus 3. All right? Just a thought. You can take it or leave it. I wanted to give you back your bonus quiz. I have not recorded these, so the way this is going to work is I'm going to give them back to you. You keep them. You bring them back to me tomorrow, and I will give them. I will add the points to the to this test. All right. And so that the bonus points will be recorded on this second test, if that makes sense to you. And that way you can look at your bonus quiz, and I did write some comments on here. Not too much, but anyway. Do you guys have questions? That's pretty much all I have to say. I don't want to call names while the, you know. And unfortunately, I can't hand it around because we have federal regulations that say you can't see another person's paper with a name on it and a number because that's so offensive to people. How many of you are actually bothered by having a paper with your grade and name on it passed around the classroom? Show of hands. One is bothered? Okay, very good. Actually, I guess asking this question to you is a violation of the spirit of the law, isn't it? Yes? It depends on the grade. I don't know. It's very bothersome to me because I don't know. So so what you're saying is I just need to give everybody an A, then I can just hand. Okay. Yeah. Oh, listen. I was going to tell you guys on the math battle. On the math battle 2. I have not announced winners and losers on these battles yet, but there has been a clear winning team on both battles so far. Although the margin by which they won was much smaller on this one. Like I had 2 teams with a 12. That was the high score. One was a 12.1. So here was the grading. I'm very picky. All right, like on the math battle, it needs to be pretty close to correct for me to like give you credit for it. So what I did was I looked through all your solutions and everything, and I tried to find ones I felt like were very, very close to being correct or exactly correct. And some problems are more picky than others. And if it was correct, I put a check on it. All right, if it wasn't correct, I put an X. And so I counted the number of checks. That's the number of points you got. I think the maximum anybody got was 9 checks. And then I took that and I added 3. All right, so that's the score. So I think because I don't want your grade to get destroyed by math battles, but I think that a lot of teams in here need to be more serious or try harder on the next one. Like I think people can do better, get more of the problems on the next one. Partly because the next part of the material you guys are going to do better on. It's more calculational, less theoretical. So that's more your happy place, right? Right? Yeah. Right. So you guys have any questions for me? Yes.
I'm still a little confused on the epsilon n argument.
Epsilon n arguments. So in what sense?
I looked over some examples and sort of get the ones where they convert to 0, but I don't really understand
where they diverge? So pick on something relatively simple. Limit n goes to infinity of like n cubed plus 1 equals to infinity, right? How would you show this explicitly, right? So let's see here. So here's scratch work, all right? And I haven't forgotten about the problem on the other board. I just forgot about it until like 3 seconds ago. Okay? So what you want to do is you want to find a big N such that if n is bigger than the big N, we get that n cubed plus 1 is greater than m. So I have to like think about an arbitrary positive big M, and I want to choose some choice of like the big N, as in nanu, such that whenever little n is bigger than the big N, I get this inequality. In other words, I can show that the values of the sequence are unbounded. I can make them bigger than any positive m I pick. So I look at this. This gives me n cubed is greater than m minus 1, right? So, or m minus, I like to think about it this way, right? So if I take, is the cube root an increasing function? If you think about it, yes, cube root is an increasing function, which means it preserves inequalities, at least for positive inputs. So I can take the cube root of this. So it looks like I want to make n equal to, you could call this the ceiling of the cube root of m minus 1. In other words, next integer which is bigger than the cube root of m minus 1. Now, all right, this is just like, you know, the man behind the curtain, so to speak. Let me write the solution over here. So this kind of one should always begin with the following. Let m be greater than 0. Right? Because you have to demonstrate that you can make the values of the sequence larger than any m. So you should declare this big M, it's a positive number, right? No strings attached at the start of the proof. Let m be positive. Choose n, big N, in the natural numbers such that big N is greater than the cube root of m minus 1, right? Alternatively, of course, I could just say let n equal the ceiling function of the cube root of m minus 1. This accomplishes the same logical goal. The point is I want to pick a big N that's bigger than the cube root of m minus 1, right? Period. Let n be a natural number such that little n is greater than or equal to big N. Then what's that mean? That means little n is greater than or equal to big N, which is greater than the cube root of m minus 1. So in the purple proof, I'm going to go through the same logic, but essentially kind of like I'm unpacking this. It's the reverse logic. So, okay, n is greater than or equal to that, right? Thus, hence, n is greater than the cube root of m minus 1, which of course implies that n cubed is greater than m minus 1, which implies that n cubed plus 1 is greater than m. So what I've shown is that any n, little n, beyond the big N, makes the values of this sequence larger than m. But since m is arbitrary, this proves by the definition of infinite limit that the limit is as advertised. So therefore, the limit as n goes to infinity of n cubed plus 1 equals to infinity. Yeah. No, just the purple part is all I need to grade. So, but it's fine if you put scratch work. Just like, you should like draw a line or something to separate your work, so I know which part's the proof. Then those of you who had Dr. Sprano for Calculus 1, you're familiar with this kind of, yeah. You've seen this before, yes.
So to do it for zero, you just do some process, but it's with the equals.
For going to 0, the thought process is a little bit different. Just suppose we're going the limit, something like the limit as n goes to infinity of, let's say, a sub n equals to L. The proof template is something like this. It starts with let epsilon be greater than 0. Then you choose n equal to something, stuff, relevant to the problem at hand. And then you say, suppose little n is greater than or equal to your big N, right? And observe that the absolute value of a sub n minus L is less than blah, less than blah, less than eventually epsilon. And this is using logical relatives to the stuff. I mean, that's kind of a blank template. You start with being epsilon greater than 0. You choose an n, a big N, that will give you the kind of inequalities you want. And then through a series of steps, you show that a sub n minus, the absolute value of a sub n minus L is less than epsilon. That is a big picture of what the proof looked like. Now, how do you actually, what's the actual process of solving it as a student? Right? You can't just do that, right? Because you don't know what stuff is. So what's the actual kind of mechanics for you as a student to do one of these problems? Probably I need to pick a specific problem. How about this? Limit n goes to infinity of, I don't know. I guess I'm going to try to keep it relatively simple here. 1 over n equal to 0. It's almost too simple, but so here, this is my a sub n, this is my L. I want a sub n minus L to be less than epsilon, right? So that looks like 1 over n is less than epsilon in this context, which suggests what I need is that this is really just 1 over n is less than epsilon, right? Which is n is greater than epsilon. So I should choose big N to be the ceiling function 1 over epsilon, right? Sorry, I can't do math. The ceiling function of 1 over epsilon. So then the proof would be something like this. Be let epsilon be greater than 0. Choose n in the natural numbers to be larger than 1 over epsilon. Consider n in the natural numbers such that n is greater than or equal to n, right? Hence, the absolute value of 1 over n minus 0 is 1 over n, which is what? Let's see here. I need to collect my thoughts here. So I had n is greater than or equal to n, which is greater than 1 over epsilon, right? So what's that say? 1 over n is what? this implies that 1 over n is less than epsilon. So I've shown that the difference of 1 over n and 0 is less than epsilon for all n past my big N. Therefore, the limit as n goes to infinity of 1 over n is equal to 0. Right? We should really talk more about this sort of thing. Where we're talking about the, the top 5% of this test right now, like the bulk of your test is on convergence and divergence of series, right? Or the proofs that are like the homework, yeah? So, can I go on? It's been a long break. Yeah. So, two things I can tell you about these proofs that are kind of a no-brainer. Your proof, if it's correct, will begin with let epsilon greater than 0 for this kind of problem, right? Or let m be greater than 0 for this kind of problem. Right? Past that, it's details. But if you can at least start the proof correctly, you've got a chance of kind of like logically finding your way from there, if you think about it. Now here, you'd looked at this problem on Paul's online notes, which is lots of nice examples. Definitely one of the things I looked at as I was creating notes for my course was that website. It's a good one. But you were a little bit mystified by one of the steps he made there. And so let me try to like unpack that. So this is an example of what I would call a telescoping series. I don't think it's obvious from the outset that it's telescoping, right? What's something that would be like in-your-face telescoping? It would be something like this. Like something like that, it's just like from the outset manifestly something that's probably going to be telescoping because it's based on taking a difference of the same kind of formula shifted by a couple terms, right? It's not obvious here at the start that that's the case, but after we do a little bit of algebra here, partial fractions, right? We can see that what is A going to be and B going to be here? Let's see here, if I put n equals to 1, I get 1 is equal to 2b. If I put n equal to minus 1, I get 1 is equal to minus 2a. So apparently b is a half. A is minus a half for this problem. Let me write it over here. So what I have, we're really looking at the sum, n equals 2 to infinity, right? Of 1/2 of what? 1 over minus 1 over, what is it? So n minus 1 comes first, right? Now, in Paul's online notes, he uses I as an index for the finite sum. One of the traps here, notationally, is to get, you really kind of want to use a different letter, right? Because this is, by definition, what? The limit as n goes to infinity of s sub n. What is s sub n? S sub n is the nth partial sum. So the notation that Paul's online notes uses in the problem you're showing me is this. Well, let me call it a sub n here for a moment. This is a sub n. Excuse me, a sub I. This is a sub n. This over here, I would want to put an a sub I. But the sum goes to n. I've often used k instead of I in this class. All right. But here we go. Sn sum I equals 2 to n of 1/2 1 over I minus 1 minus 1 over I plus 1. Okay? So first of all, there's a half. I hope we've learned our lesson, like, do you want to put a half on everything? No, 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 no. We should take that half, and we should, like, put it over here, right? And make some big brackets, and just keep the half out front. Just, all right? I equals to 2, what do we got? 1 over, what's 2 minus 1? So we get 1 minus, what? 1/3? And then I put in I equals to 3, what do I get? 1/2 minus what? 1/4, yeah? And what's next here? So this is I equals to 2. This is I equals to 3. I equals to 4, I get 1/3 minus 1/5, I think. Let's see here. I'll go to I equals to n minus 2. What's that give me? N minus 2, I get 1 over n minus 3, thank you. Minus 1 over n minus 1, yeah. And then I equals to n minus 1. I get 1 over n minus 2 minus 1 over n, yeah. And then finally, the last one, I equals to n, 1 over n minus 1 minus 1 over n plus 1. So you're asking me where that formula came from in the notes. That formula came from going through these details for the nth partial sum. And that's why we call it telescoping, because if you work out these details, you can see that after we make the partial fractions to simplify the thing we're summing, there's the systematic cancellation, telescoping, and what's left? The thirds cancel, right? There's a fourth that cancels with something over here. There's a fifth that cancels something over here. But the 1 and the 1/2, they never, right? These survive. And that's a general pattern that, as far as I know, for the examples I can think of, always happens. If there are two things that survive the start, there are two things that survive the end. So over here, I've done enough that you can, I think you can see the pattern. Like this n minus 1 cancels that n minus 1. This n minus 2 is going to cancel n minus 2 I didn't write, you know? And you're just going to be left with these two guys. Kind of, I sometimes call them bookends. And so what's 1 plus 1/2? 3/2. So I get 3/4 plus 1 over, or rather minus 1 over n minus 1 over n plus 1. That's still, I forgot my 2, right? Let me multiply the 2 through if you guys don't mind. 2, yeah. So here you go. This is a formula, a stone cold formula for the nth partial sum. And then how do you calculate? If somebody gives you a formula for the nth partial sum and says, what's the series converge to? Or does it converge? What do? Take the limit, right, by definition. The series converges if the nth partial sum converges in the sense of a sequential limit. So what happens is n goes to infinity here. Right, this goes to 3/4. And so therefore, the series sums to 3/4 here. Yeah.
So if you have that problem and you have nothing else to you can't use a test or anything, you need to use a telescope. Can you calculate it to prove that it's convergent?
Well, so I will.
Or will you say calculate the?
I usually give instructions, calculate if possible. And the if possible, it pretty much boils down to it's something that's in your face telescoping like that, It's something which allows partial fractions like the example I just did, or it's geometric, or it's some simple combination of these things. That's all we can find the actual sums for right now. Other than that, now, would I give you, if you didn't see that for some reason, and instead you did limit comparison to p equals 2 here to show it converges, I'm going to give you significant partial credit, right? But there, and I often do ask a telescoping problem. It's an expected type of problem on this test for you. You should be able to work it. Yep.
Here, compared to p equals 2 series, you have a series which is bigger than something that converges.
Oh, but if we did limit comparison, limit comparison, L will work out to 1. If you do like 1 over n squared divided by this, it just gives you, after you simplify, basically n squared over n squared minus 1, which limits to 1. This would be the unexotic case of the limit comparison test, in contrast with what I started with today. Well, anyway, I will see you guys tomorrow. Don't forget, you need to know the series convergence divergence tests, but I would encourage you to look at that video that I sent before. I think that has a good strategy. Hope it helps you. Let me give you back your, can you hit the, can somebody hit the